có nhiều người đã ghi đã làm như vậy. Còn những cái lúc trước thì để coi. Thì lúc trước cái lecture 4 thì mình có 62 người vào, thì cũng để mở cho mọi người vào. Thì lecture 3 là có 49 người. Nhưng mà nếu bây giờ tôi vẫn để cái lecture 3 pre-assessment mở, thì nếu mà ai có thể vào làm được thì cứ làm để cho mình thử nghiệm. Nói chung là cái lecture 5 thì như vậy đó. Thì có nhiều những câu hỏi này 13 người không trả lời được, là chỉ có 13 người trả lời đúng. Thì cái này có thể là gì, standard cell utilization should be as high as possible. Cái này thì nó chắc là tại vì cái English nó người đọc không hiểu, có thể là hiểu lầm, nhưng tôi có thể là go over cái đó. Còn chip aspect ratio là bề ngang trên bề cao, thì mọi người không có rõ cái chuyện đó. Trở lại, có nhiều người thì cái này tôi không biết cách xếp hạng như thế nào để mà đưa 100 điểm lên trên. Thì có gì thì sẽ nghiên cứu sau. Chỉ có vậy thôi. Thì rất cảm ơn mọi người đã tham gia vào cái pre-assessment này. Thì bây giờ mình bắt đầu cái lớp học. Okay, thì hôm nay
in progress.
So today is the lecture 6. So, oops, wrong. Is that no? It should be lecture 5, right? I always got confused. Right, Tian?
Yes, I think so. B5, right?
Yeah. So I always have to be one step ahead of the class. Okay, so today is floor planning part number 1, lecture 5, lecture 5, and we're going to discuss the die size definition and the IO cell placement. So, so an overview. So we have, we have done the import step. Today we're going to go through and do first real floor planning steps by placing the IO cells and defining the chip size. So the output will have all these different things, but today we're gonna cover the top 2. Right. At the end of the floor plan, you'll be ready for the cell placement. So first,
And Phil, I can't hear you. I was wondering if anybody else can hear.
Yes, we lost on Phil.
Okay, let me call real quick.
Everyone, we apologize for the technical difficulty. And Phil will get back on as quickly as he can. Until then, I want to make sure that we get some of the communication of some other issues brought up. We've created email groups for each of the different regions, North, Central, and South. You should be receiving a message today with instructions on how to communicate with the other students participating in your lab area to facilitate communication and to help us answer your questions. I'll need the lab assistants at each of the locations to reach out to me independently and let me know the region that you're supposed to be contacting from, and that you'll be the primary contact for that region. So all the TAs will be receiving a message about that. But at the locations, Hanoi, Da Nang, and Ho Chi Minh, we'll need a primary point of contact to make sure that we're addressing the technical issues that have come up. I apologize for some of the communication problems we've had making that work. That was the primary logistical issue I had. If anybody's got any questions, you can feel free to ask them at this point while we're waiting on Phil to be able to get connected again. And I see a question has come in. Bach or Tien, this is your guys' expertise, not mine. So if you guys see it in the chat, the chip aspect ratio we see in the video was AR equals height width, not width height, like the result is on the VLSI physical design floor plan at 315. Is the video wrong or is something happening?
Hey guys, sorry, I got the internet problem, so I'm logging in with a hotspot. Hopefully that's okay. Can you hear me?
Yes.
Okay. Let me share again. Okay, can you see the screen?
Yes, we can.
Okay. Is that the right screen? Placing the IO cell?
You see placing the IO cells across the top and then 9 slides on display.
Okay. All right, so sorry about that. So specifying the floor plan will be, you'll be using a command called create floor plan. So at first you do the core utilization, you want to do the IO, the forward, so Tien can cover this. But when you read in the import, we already covered there's an IO file that specifies the location of the paths that you're gonna need to place. This show both the rectilinear block level, but before we have the chip level IO file that we already went over it. So you can either use a read IO file or you read the def file. But this we already went through the IO file. We have the edges, the left, the top, the right, and the bottom, and also the top left, lower left, bottom left, and top right, bottom right for the corner cells. So you will define the different instances of the corner cells and what signal it connect to. So we already have this cover in the import step. But today we're going to dig a little bit deeper on the type of IO cells. So the IO you can see is going to have a standard height, but there are different types of IO cells: the digital, analog, and power and ground. And also there are some special cells for electrical interface standards that we're not going to worry about. But in addition to these cells, we have a corner cell and filter cells. So the digital cell, the digital IO cells usually is the input, output, or input, output. And in addition to the drivers driving in or driving out, it has some ESD protection, and it has pull up or pull down as needed for the IO functionality. So the ESD protection, it is something that we're not going to worry about, but we're going to touch on it a little bit when we reach the other cell. But then the analog IO cell is just a wire, and it also has the ESD protection, including current limiting resistors. So it just has a pad. And then you have power and ground cells. pound ground cells is again is only just like an analog cell. It's just a wire with a pad. But the pound ground cells, like any other cells, usually you have four lines of the IO cells have the VDDIO and VSSIO. The IO cells usually have higher voltages, so they have their own power and ground, very noisy. And in addition, you have a pound ground of the core, going in a ring, and everything is continuous. So you have ESD structure buried underneath here as well. So the IOs, if you have an IOs, the IO cells sink and source a lot of current, so have a lot of noise. So you want to isolate from the core VDD and ground. So in terms of ESD protection, just a general concept, right? You have a pad coming in the outside world, it can be a very high voltage, but inside your core devices, you have very thin gate oxides of P and N channel here. So if there's a spike here, if you don't have protection, then you will break down the gates here. So protection usually have diodes. You call clamps. And then you have current limiting resistors. So in general, the concept is that when an event happens, the protection, secondary protection turns on first, and then the current limiting resistor will help limiting the exposure of this device, and then the primary ESD will turn on, therefore protecting your circuit. So those are power supply cell. And in addition, you saw the other picture. You have corner cells, the corner cells, and then you have filler cells. Corner cell is nothing except for the continuation of your power and ground wires with some bending here for current, minimizing current crowding and improve the EM performances, etc. And the filler cells are, if you have IOs and they like standard cell, they have placement areas, and where you don't have IO cells, you have filler cells, just to make sure the anything that needs to be continuous will be continuous in these filler cells. So there they are. And in terms of IOs, placement of these IOs, we need to make sure that the space between the IOs and the corner cells is affected by what we call bonding wire rules. There's a certain spacing between the wires or at the corners, and there are packaging rules that need to be followed. So location of these IOs will impact that. So when you place the IOs, you need to be aware of all these different requirements. So this is an example of all these bonding, the pad being bonded by the bonding wire to all these pins, all these packaging pin. So that's about the IO cells. But if that's a chip level, but sometimes you have a place around and you have the block level. So you at this block level, then you place the IO pins, not the pad cells. But apparently it's at the block level, there's no pad cells. So you place all these things and you define what we call PR boundaries, the boundaries where you do and place and route. So you place all these things, these pins, and you usually consider where they are to minimize the signal delays if there are fast signals, and you will space them, put them so that you minimize the wiring and congestion, etc. So just some general concept. So that's placing the IOs. And then before you place an IO, you need to know the chip size. So this is part of the floor planning. How do you determine the chip size? So first of all, the chip aspect ratio is something that you need to pay attention to. In general, you want to be as close to 1 as possible, because that's the that sometimes is the best configuration, but it all depends on many factors. But is it width versus the height, or sometimes it's defined as horizontal versus vertical routing resources. And then the chip size is determined first, the I/O ring area. I/O ring area is determined by the height of the I/O cells you see is rotated. So this one is fixed because of the I/O cells, and then it's called core to I/O spacing area. So between the I/O and the core, there's some spacing error requirements that just put the core devices away from the noisy I/O, and sometimes there are some DLC rules that you need to follow in regards of spacing certain structure away from each other. So you need to take that into consideration when you determine the chip size. And then inside here, the blue is core, that's called core area. So the yellow here is the I/O area. And the core area between them is a spacing. So in the core area, so you so in the core area, you estimate the core area based on a few things, right? One is that somebody admit. Okay, so so when you come in, when you read in the input from netlist, you have certain areas, macro areas and standard cell areas as used by the synthesis tool, and then you will, in the placement route, you do a few things, including the clock tree synthesis, where you add buffers and inverters to build your clock trees. That requires some additional cells. And then your timing optimization, sometimes you increase the cells, or you do different types of cells. So you have some areas allocated to fixed timing. So these are additional cell area that you need to calculate, add to the calculations. So usually it's about 10 to 20% of your incoming cell area, depending on how difficult it is to do the CTS or the timing optimization. So, and then on top of that, there are something, as you learn later, there's something called macro padding and halos, things that you put around the macros that you cannot place a standard cell too close to it. You'll learn you learn about that, but basically you have to have some blockage area where you cannot place the standard cells. So that you have to calculate. And then there's some unused area due to your irregularity of your floor plan. Sometimes some areas that you don't need to use. And then last but not least is the empty area between standard cells. So this relates to what we call standard cell utilization. So if you have a placement area of a standard cell, maybe I can zoom in a little bit. So if you have a placement of a standard cell, if it's 100%, then you don't see any hole. But if you do this, chances are for sure you cannot route. The reason being that the signal routing is on top of the cells. If you have so dense of a cell, there's so many signals in an area, you cannot route without violating the DRC, the design rules. So it's too small. So you have to spread the cells out. So you see here, there's some empty here. So this is the spreading of the cells out is to reduce what we call congestion. And you'll learn about congestion later. But basically to do this so that you have enough space within this area to route all the signals that you need to. So it's called low standard cell utilization. So the most meaningful thing that you see is this standard cell utilization. So you have all these different things outside of it. So you have a standard cell placement area. You have a row, lots of rows here. You will learn about it. But basically, the standard cell utilization is defined as a total of standard cell areas that you need, and divided by the total placeable standard cell area, meaning, I guess that's obvious, right? So if you have 50%, then you have 50% empty and 50% occupied. 80% or 20% of the space is empty. So these things, in addition to routability, it has some signal integrity impact that you learn. When you're so dense, the coupling gaps between signals might have an impact on ability to close timing. So you want to okay, thanks for the feedback. I was told to slow down. So due to the coupling gaps between signals, you will need to sometimes you have to have lower standard cell utilization just to close timing. You learn about that. So so those are the different things. So this is important that you know how to estimate this to give it a very good starting point. And you can see here is iteration. This is a floor planning iteration process, meaning you try and error. You give a die size, and then you go through and you do all these analyses. You do all the placement of all the cells, and then you analyze the congestion and say, hey, this is not doable. You go back and you increase the die size, or if it's too loose, and you decrease the die size. So it's an iteration process, like the place and route process iteration, meaning you don't just go through once, you iterate, you go and you analyze and you redo, right? So that's a methodology. But after knowing all these, but there are some limitation of the die size estimate. If your design have a lot of internal circuitries, what we call core circuitries, that has macros and has standard cells, and you have this many IOs. After you put the IOs in, there are space between them. So that means that if the core area is smaller, you can shrink the die, but you can't, because you have so much going on inside the core. So what we call this one, you call core limited design. But if you have so many IOs, but so less of a logic, all your logics fit in here and have empty space around them, but you have so many IOs that they have to stand next to each other. So the die size now determined by the IO spacing, not by your logic. So that's what we call path limited design. And block limited design is similarly to core limited design, except that area-wise it might be good, but because the macros are the big blocks. Because of the way the big blocks are built, sometimes you cannot fit everything in such an area that you have to increase the die area simply because of the shapes and the number of macro blocks. You call it block limited. And sometimes it's package limited. So when you choose a package, each packet type, because of cost or because of the size of the package, there's a limitation of what the maximum die size can fit, can be implemented to fit in the package. So you are limited by the maximum die size. So therefore, you call package limited. Okay, all these things. One thing is very common is path limited design. As you have chips that become more and more complex, there's a lot of IOs, memories and everything interfacing to the outside world. So there's solutions for path limited designs. There are many, but some of the typical ones are. So this is how you normally would do the IOs, called inline IO placement, where you have one path and then you have the path logic, ESD, IO buffers, input buffers, output buffers, etc. But if you have path limited, then you can consider something called and you have alternate path circuitries here. So so then you can fit more. You can fit more in one area. And what this one is called non-cup. Cup is circuit under path. Yes, there's a technology called circuit under path where all your ESD or your buffers are put under the path. So therefore, you don't have this blue path logic anymore. So you can still do staggering of it. So the idea is to put more in the same length or width. So in here you see this multiple paths that's sitting next to each other. If you do one line, it won't be it won't be fit, won't fit. So it's called stagger path. And sometimes you have double bond, meaning that sometimes you one signal like VDD or VSS for signal integrity and for power purposes, you can do two bond wires into one signal. So and also another solution for path limited design is called flip chip. So flip chip is something that as they indicate, your die will be flipped and your IOs, instead of being on the side, it will be on top or at the bottom of your die, meaning this is your circuitry is placed on cells underneath, and you have these what you call solder bumps. Yes, these bumps are really looking like this. So when you connect to the board by these little solder bumps, and so this is a way to have a lot of IOs without being limited by the paths. So I think that's all about die size estimation. So in addition, the die size in black. In addition, you have something called seal ring and line. So seal ring is the type of structure that so yeah, let's do seal ring first. It's a type of structure that give your device some physical barrier. So if you can see here, the in between dies, when on the wafer, when you cut them, you do a saw. So let's talk about that first. Okay, so scribe line is in blue. So scribe line is outside of the seal ring. So this is where you can guide your saw. It's called dicing, wafer dicing. So there's a blade that go through the blue line, and then you will cut it. You cut twice, cut the big one, a small one, but you don't need to worry. So basically, the die can be sawed off the wafers using a blade or using laser, or the most advanced using the plasma, which is like a chemical process that separate the dies from each other. But when you saw it, when you saw it outside here, usually there's some stress that will if you don't have a protection, will crack your die, or when your chip is being exposed to the outside world, sometimes moisture can come in. So this is a physical structure that built is called seal ring. So the seal ring is built by having various vertical structures, mostly metals, and then some isolation structure. So that you don't need to worry about these, but basically there are many different types, but mainly they use to protect your circuit, your die. This is your active device. So by having this physical area, you can stop the the materials from the soil or stop moisture or other contamination going into your circuit. And because of the SCO, it has some structure like this. So sometimes it is a problem of having transmit all the noise by internal circuitries and go travel across this SCO. So in some sensitive design, the SCO is, instead of continuous, they have gaps in between them. And then if they need to, they can do double seal to protect certain circuitry. So it's not all the SCOs are continuous. So I think that's all you need to know about sealing, and that's all you need to know about this step. So in summary, you have done these things. You estimate the die size, you define the chip width and height, and you place the IOs or pad. So at the end of all these commands, you have some database, something like this, right? So IOs are placed, and your target utilization on your logic here and all your macros on the right unplaced yet. So at this end, you will be ready for the next step called macro placement, which is the third step on this process. So some note in here about the die size estimation. This is a formula, and it has some numbers that you can plug in to just give you a guidance, right? So it has gate density per square millimeter. It's called D. It has a number of horizontal layers, vertical layers. It has a gate count, not including macros, because this is used for the standard cell utilization. It has IO areas, and I has macro area. It has target utilization, and then it has additional gates for CTS and timing optimization, including ECO to fix timing problems. So all these things you plug in here to get the die area in square millimeter. So that's some rule of thumb that you can, you can use. I think that's it for.
If you may add a comment here.
Yeah.
Yeah, so the die size is very important. So when we design and productize a chip, the most important thing is we want to build a chip that can make the most profit, right? Meaning that it had to cost the least. So we want to optimize for the smallest die size as possible, but still meet the chip requirement. So like the die size is, if you can go back to the formula that you just showed.
Oh, formula. Okay.
Yeah.
Sorry, I thought. Okay.
Yeah, the first factor, the density. So depending on the technology, geometry, like the 16 FinFET, for instance, you're looking at about like 2.8 million gate per square millimeter. And again, depend on the fab or the that you work with, like TSMC or Samsung or Global Foundry. You're looking at somewhere about like 8 to 9 cents per square millimeter. And from there, you multiply up. If you had a chip like 20 square millimeter, you're looking at like maybe almost more than $1. And you add the cost of packaging and the test time. Test time is the time that the chip will be on the tester. That's also add to the overall cost of the chip. And you from there you can estimate the cost per chip. Again, back to the die size is very important factor when we start to design the chip. Actually, when we start to architect the chip, we already estimate the die size of the chip and see if we can make money before we can start the project.
All right. Thank you, Vu. So by the way, Vu is a and he's architect and a product definition person for NXP products. So he has a ton of experience in terms of system level definition, defining the chips, what kind of chips that NXP can make, and also now is defining the whole product line. So we're lucky to have Vũ, in the teaching team here, in teaching staff here. So in the future, you all have aspiration to define chips and start up a company. Yeah, make sure you contact Vũ. Yeah, thanks Vũ for the comment.
You're right.
Yeah. So any other people who have comments or you have questions? So I meant when I say we're very happy to see questions from you, and like we said, học và hỏi, đúng không? Yeah. Cách trả ơn cho mấy thầy cô đây là dạy miễn phí, không biết các em có biết không? Thì cách trả ơn cho mấy thầy cô là bắt đầu hỏi. Nếu mình hỏi thì mấy thầy cô biết là mình hiểu mới hỏi, mình không hỏi là mình không hiểu. Ít khi mà mình không hỏi mà mình hiểu, thì học thì hỏi, thì càng hỏi nhiều thì các thầy cô càng vui, nhờ các em cố gắng hỏi.
Phil, we've got a question in the comments that looks pretty good to me. Core to IO spacing is determined by design rules. Can you talk more about this design rule? Is there anything special we need to notice when we design it?
Yeah. So this core. So to be honest, I don't pay attention to those rules when I do this core to IO. And granted, I'm a manager for a long time, so I don't have a hands-on experience in this. I have to refer to Bat or Thieng, who has more experience in terms of doing this days in and days out. But my understanding is when you have the rules are determined here, and sometimes it can be by design as well. So basically, if you open the design rule, there are rules that say active area cannot be this many micron away from a noisy transistor, for example. That's one of the dominant rules that I remember. But there are some other rules that I don't remember specifically. So Tien and Bat, do you have any additional, or anyone, Vũ, you have additional specific rules that they should be worried about, other than just going through the design rule manual and see?
Yes, I want to add that I think within the chip, very much you just follow the design rule, right? But then on top of that, every chip, especially when you have the digital portion and the analog portion, and then by experience, you need to essentially keep those two things separate, right? But those like your own, experience, by making so many chips, say, okay, if certain things switching right here, it's going to affect my digital portion. So how do I, essentially isolate that? But in terms of, let's say, you look at the DRC from the play TSMC, then it just you just follow those, manufacturing rule, just DRC. So anything on top of that is based on the experience, right? And what type of chip you do, and then essentially you have to understand your design a little bit more, right? Certain things happen here, it's going to affect a certain other portion of the chip, right? Let's say, you have a radio in one corner, so more likely the analog designer, gonna say, wow, this radio has to be in corner, right? It has to be very quiet. So everything else has to be, somewhere else, right? So those come from the experience, and that's a little bit. It take years of experience to know where to place things, right? And you have to understand um, the circuitry, right? It's just a lot more than just purely DSC, right? Just to manufacture things correctly. So that's two different layers there. So
Thank you, Tien. But you have any comment?
Yeah, so in addition to what Ting said, I know for some of our chip, that area we use for chip that has a lot of memories that require a lot of power. So we use that area sometimes we widen it to accommodate the power rings in that area. So that's sometimes we use that. So
Yeah, thank you. But so to answer fully, what I'm going to do is that I'm going to look for a design rule manual, and I'm going to point you directly to what rules might have the maximum, the most impact on this core to IO spacing. And in addition, when we cover the remainder of the floor planning I will share with you what we do in real life to isolate the core from the IO cells and to collect the noise generated from the IO cells. That will be related to the protection around the core, but not specifically related to core to IO spacing, but just to add to what Tien said about the practical experience that doesn't go into different areas. So the next question, can you explain more about the filler cell? What inside the filler cell? So the filler cells, like the standard cell filler cells. Let me see, where is the filler cell? Do have a lot of backup cell? Or maybe let's try this one. So a typical cell, right? It has a pad. It has ESD protection logic, pad logic, ESD transmitter, and there are wires going on top of the pads like VDDs and VSS of IOs and VSS of core, etc. So when you don't have a cell like this, and you have a next one and you have an empty space in between, the VDD VS have to be continuous. And sometimes there are wells or not sure the IO pads have wells or not, but there are structures that need to be continuous in a ring like this. So that's really where the filler cell would look like. So at the minimum over here, the filler cell will have all these wires, 4 wires, so just go horizontal like that. So when you place one next to the other, the whole thing is continuous, like you see here. I hope that answered your question. But when we do the lab, if we lucky, we have internal of the at least the Tien may be able to show you what the filler cell look like in terms of just metals, and you can see. Right. And the next question, I would like to know why we choose a wafer to be round, not square, rectangular shape like the chip. So if you it has something to do with how the whole if I can draw, let's see. No. So you can see when the silicon is made. So silicon, the wafer is made of silicon, right? It's like where's oops. so this entire wafer is silicon. But why it is like that? Because this is almost like 100% silicon. But you know, silicon is made from sand, right? And the way they do sand is they grow something, a cylinder. They grow from sand to some shape like this, just to get to the pure silicon, and when they do that, it's a cylinder, and then they cut along the cylinder into wafers. So you can see wafer is going to be on wafer like that. So it's a manufacturing process. It has something to do with how the silicons are made from sand. It's growing. Right? I hope I answered that question. And then the next. Next question is, could you talk more about the relationship between the package limited design and the die size estimation? What kind of package are we talking about? So package, the choice of package is really determined by the marketing team, right? So say if you have a target your target market, and we can talk more about this. So if you say I can only sell with this cheap package, right? If I go to a very expensive package, I go to flip chip, then I cannot make money. So because of the market demand, we can only make money if we do in this package. And the package usually comes with a maximum die size, because for obvious reason, you see in here, if you see the package here, right? So the package means all these things are already fixed size. So if you grow this die size too much, it'd be too close, and all these bonding wires will be too close to each other, violating all these manufacturing. So Vũ, and you want to add more to that answer?
Yeah, so the yes, right. The packet type have direct impact on the cost. For example, a wire bond package like what you're showing here, depend on the size of the package, it costs somewhere between 16 cent to 35 cent a package. It could be more if you have a larger package. The flip chip package is pretty expensive. You're looking at the minimum 50 cents a package. The difference is that for the wire bond package, the fastest signal, probably a DDR type signal, you're looking at the maximum frequency at like 650 megahertz. Technically, it could be a little bit higher, but for 800 megahertz I/O is not possible. So if you design a chip that support like LPDDR4, which can operate up to like 2.1, 2.3 gigahertz, then you need a flip chip package, and you pay extra cost for that.
Yeah, and sometimes there are thermal considerations. There are different considerations for system level. If you design a chip to be in certain equipment, there are some footprint requirements you have to have. And in the future, you see this 2.5D, 3D system in package, where you have very advanced but very costly. So next will be, could you talk more about bidirectional paths compared to input-output paths? They're the same, right? So a bidirectional mean input and output. So
just most I/O path on the chip bidirectional, except for some special path. For example, you have the path for tamper detection, the most likely output There are also tamper detection the input if you support an active mesh of detection. But there may be some special pad, for example, test clock, where you output the clock for testing purpose. That could be made either bidirectional or just an output pad. But typically on the typical microcontroller or microprocessor, most of the pad input output. Some special pad that output only, for example, for the DDR clock, that is output only pad.
Yeah, what it means that sometimes you only need input or output, but you use a bidirectional path because you're not saving anything. So it means that if you input and you disable the output. But the answer is bidirectional and input-output path is the same, right? All right, feel free to ask more if we don't answer your question, but I'm going to go on to the next one. In the video you give us, it say that flip chip costs so much more than wire bonding. Is it just by technology or by something else? Is there any special case we can use flip chip because it's cheaper than wire bonding? I would say the answer is no, but Vu, can you comment on that?
Yes. So the flip chip, it typically is cost more. It just costs more to for manufacturers. It's also cost more the material in to bond the wire from the pad to the chip itself. And flip chips also that it typically what you call it, the yield, it's also less than wire bond package, meaning that when you build the packet in the chip, I'm sorry, the chip in flip chip package, there's a more part be fail. The ratio of the failing rates are higher than the wire bond package.
Yeah, so as you can see, it's fancy, right? So you put all these sort of bar in your package, and you put this pad on top of your layout, and usually this is very big chip, and you have lots of IOs.
Yeah, the other thing I would add is that because typically the chip that built in the flip chip have a high speed memory interface, high speed IO. It's also meaning that they are usually a big chip and they require a larger package, and they usually sell at the higher price. And that's why people, the manufacturer would charge more money on top of that.
Yeah. All right, thanks for all the questions. Appreciate it. Make me happy. All right, so please keep on coming. So especially what we want to request the TA is that we're going to share the result of all these pre-assessment, right? And if please take a look what your team doing and bring in the questions, right, from your team to help us help your team understand more. For people who does with 35 points or 50 points or 70 points, the goal is for them to understand it all. So eventually, all the students need to understand so that we can do projects, right? So this is a time where you can ask questions to understand, because in the midpoint, you're going to be given projects. And if you don't understand, you will not be able to finish the project with good results. So do use your TA and do ask questions so that we can answer to help you understand it all. Okay. I think it's almost 9, so maybe we can take a 5-minute break and go to the lab session. What do you think, Dave? Okay.
think I lost my mute button. Yes, I started a clock. We'll be back in just over 5 minutes. Let's start at 9:05. Oh, I'm sorry, at 10:05 Vietnam time.
Yeah, and in the break, if you have come up with some other questions, feel free to type in and we can answer either on chat or bring it up live. Thank you.
She excited for you? Okay, Mr. Green. Get him. Okay. Green don't get it. Everyone will be restarting in about 2 minutes. We will restart class in about 1 minute.
Okay, looks like right.
Yeah, I think we're ready. And Tian asked us, the students in the chat, if any of the TAs or students were able to run Lab 3. If you could answer him in the chat, we'll get started, return to the lecture.
Yeah, so the lecture is done before Tian starts the lab. I just want to thank Bud for correcting me in terms of the aspect ratio is actually height over width. So I have corrected the lecture, and I will update the one in the Google Classroom accordingly. Go ahead, Tian.
Hello, chào mọi người. Thì hôm nay mình sẽ làm cái lab 3 thì let me see here. Thì hôm nay mình làm cái floor planning thì ở trong cái chat á, Thiện có hỏi là không biết là mình đã có cơ hội làm mấy cái lab chưa? Chưa thấy ai trả lời. Anyway thì hôm nay là thì cái lab này nó có 2 phần, tức là hôm nay thứ ba với lại ngày thứ sáu thì cái phần 1 okay, phần 1 là mình làm về cái IO placement cộng với cái macro placement. Đấy. Rồi sau đó là cái phần 2. Cái phần 2 tức là ngày thứ sáu á, mình sẽ làm về cái power, right? Power power read, power and route. So okay, so for today we just do the part 1. So I'll just quickly go over, the important file that we should pay attention to. So, we have this course like Lab 3 floor plan 1. because it's gonna be floor plan gonna divide into two weeks, right? This week and then next week. So that's why we have floor plan 1 and then floor plan 2. So next week gonna be floor plan 2. And so under here we have data. So this is very similar to the lab 2 that we did last week. So we have essentially just the input, right? We have a net list. We have the MMC here, and then we have the IO, the pad placement, right? The main documentation is going to be under the doc directory. So actually, I make a mistake here. This is not, it's not MMC. I need to change that. But and then just to make it easy, so I split the big. So we have the main script here called run lab, right? So within this run lab, we can look at it, but essentially it's have like 5 or 6 different steps. So we're gonna do like one step at a time. So it just make it easy to manage. And I also I have that for this lab I put in an Innova startup, right? So this is a file that get loaded right after you invoke Innovas. So, and here just instruction, just like we did, before. We just copy what we have here to a user directory, and then all the student and TA can work, on their own copy, right? We don't want to touch what under Tresemme. So, okay, so for part 1 here, we're gonna start the Innovas, and let's see here. So I do have it here. So I already start Innovas. And let's see what I'm asking. So, okay, so note the following information. Essentially, these are the things we should pay attention probably the first time you run it. After that, not so much. So here, let's show. So if we start Innovas, right, you can see, it's gonna tell you sorry for the delay. So I'm gonna go up one a little bit. Right here. So you're gonna see the tool gonna write out on the screen what version it's using, what machine it's running on. So that's important, right? And then it's actually even tell you how many CPU with the current license is allowed. And then for me, I have my local Innovas where I define all of these alias. And for this lab, I add in some additional, essentially I suppress, because what they have is in the library, they have some warning and error. And I don't, the first time I want to look at it, after I look at it, I don't want to see again, right? So, so that's one way you can do is, you can go here and just add all these suppress things that you don't want to see anymore, and you think it's okay, right? So make sure you look at it first, and then after that you want to see it again. So so here I can so this lab, so let's go to my copy. So I have the lab 3 here. So this is just a copy of what under Tresemme. So that's the wrong one. I should be in here. as you can see here, I split the lab into part 1 and then part 2, right? So for today we're gonna do the import. We do the list, the macros with the blockages, and then we do the placement, adjustment, right? So resizing the core area, and then this for Friday. So and I think it did mention.
Tian, just a correction.
Okay.
Friday we'll do the macro placement. Today we just do the chip area and the IO placement.
Oh, really?
Yeah, we haven't covered the macro yet. So the power grid will be next week.
Oh, really? Ooh. Okay, so let's see if I see, because that's not a whole lot I can do here. Okay, so let me try.
Yeah,
to
you
see.
can rerun the import and show them around, like the IOs, the different cells and the core to IO to core spacing and all the things that we mentioned in the
Okay. I see, because we did some of that last week.
Yeah, but
So,
this time we're gonna go deeper. Because whatever I cover in the slides, if you can show them.
okay, so the power gonna be the next week, I thought. Okay, I see.
Right.
Okay, so here just want to quickly look at what we have in the Innova Startup, right? So I just do the suppress meshes. Okay, so let's see. Let's go back here. Okay, so what I have here is do the run import. So we can look at the run import. So this is very much identical to what we did last week, right? We set it up, the PowerNet, VDD, VSS, and then we read in the MMC, where we define all the constraint, timing library set, analysis view. Right? That's for the timing information. And then for the physical, we have a list of lab file, technology lab, and then the cell lab, right? And then we read them in. So once you have those, and then the net list. So essentially, remember the 3 things, right? So timing information, physical information, and the connectivity. And then you run the init design, right? So let's run that again. So I'm gonna source. Okay. So I'm gonna switch to the floor plan view here. So by default, so far, all we did was just init the design and create the ring, right? So if you look here, we have not created the core yet. So it's by default, all these areas just get filled up with the row, right? So let me try see how much I can do for the second. Yeah, these are for the macro placement. Okay, so let's see what we can do. I can look at this one, see what they have. Yeah, because the import VAMs we did last week already. Yeah, I don't want to repeat what we already did. So I think, Phil, I think we probably just go ahead to do with the placement anyway. We can do it today and Friday.
You mean macro placement? Yeah, you can do it before I cover. It's fine.
Yeah, because
Yeah, go
I
ahead.
mean, after this not much to talk about import. It's just right. So
yeah, you
and
can
the
show the
lab is
IO.
very long, right? So the student
Yeah,
can follow these.
yeah. If you can show the IO rings, right? References. Did you show from the placement to the actual location of all these cells, and show the corner cells and show the
Yeah, we did that last
VD?
week,
Oh,
right? Yeah,
okay.
we did look at the order of the pad here, and we even tried to reorder some of them.
Okay. Yeah. Go ahead to do whatever you plan to do for today. Yeah.
Or just a portion of it. I think that's fine. Okay, so let's go here. For plan view. So for this lab, I put in like essentially two things, right? What I think you should do on your own, which is I put in the orange color here. So we have the main documentation from straight from Cadence, right? And they have the breakdown. Let's say for this portion you do like section 2-2, 2-3, and then 2-4, right? So I'm not gonna go through this because I don't want to do the same thing as what Caden want you to do. We can look at some of it. So let's say this one is page 9 to 10, right? So let's see here. So it give you a little bit more hands-on, right? So this, you go to this section and then they say, wow, you come here, mostly do the interactive, right? So this is something that you want to kind of like exercise, get used to it. But in the lab, I don't think it's efficient to do all these, so that's I want you to do on your own, right? The orange portion of it. And then we can do what I'm trying to do with the blue color here is what we want to do together to achieve the same thing, right? So what Kaden want to do is like show you the step that you can do in the GUI mostly. And what I want you to do with me, along with me here, is how we can do it with the command, right? We just run a bunch of command, and ultimately that's when you do the implementation. That's what you're gonna do, right? You're not gonna go in and move the cell, here and there. No, you're gonna run command and place the cell exactly what you want it to do, to be, right? So let's do that. So we're gonna look at the place run place ins article, run place in article. So look at here. make sure. Okay, so if you look at this, the first thing is in this script is it's create a floor plan, right? So just quickly, so right here is create the floor plan, right? Just so essentially that command is essentially the same thing as in the Cadence lab, right? You can go in here and specify all these number, right? So what you do in the lab here, essentially the same command here. So that's why I want to do the same thing, right? We want to do there's two ways to achieve the same result, right? So okay, so we're gonna create a floor plan, and then let's see. So I'll just do it slowly here. Did I copy the whole thing? Yeah, sorry about the delay. Okay, actually, before I do that, I want to make sure I put some marker here. So this is what we had before, right? So you look here, all the row is very much at the origin, right? So yeah, I put something here. I'll just do something with the IO. So if something changed, then we have a reference. That's what I'm trying to do here. Just put in a reference. Okay. So I just run this command, right? Create floor plan. And what it does is tell me the die size, right? Well, specify the die size. And then remember, we define the core site in the technology file. So in this lab, we have only one. So, but when you have multiple, then that's the reason you have to specify which size you want to use for your chip, right? That's the reason we specify here. So okay, and then okay, so that's the die size, and let's see here, 120. So that's X and Y. So that's 6,000, 5,000. And that the core, that's the offset. I think that's the offset. So if I'm gonna measure from here, it's gonna be 120, right? So this this command is say, well, I'm gonna create a floor plan with some offset, right? So that's what it does. Okay, so the next thing we're gonna learn here is what I call a relative floor planning, right? So it's so what relative floor planning is, you have an anchor, right? You create your anchor, let's say a macro, right? You start up with a macro, and then everything else gonna be reference that macro, right? So, and as you can see here, that's what they do in here is they select a macro and they place it. So let's try that. So, I'm sorry, what's gonna. No, I can't do it here. Sorry, I had to do it from this one. So the first thing is select object, right? And in this case, select the RAM 00. Yeah, I'm going a little bit slow for this. Okay, so from here, you can see in the GUI it says selected one, right? So, you know, where is that? You know, if you notice here, there's an icon that says zoom selected. So normally you can zoom out and see which one is selected, or you can just click on this icon, right? So to zoom to the macro. Let's see, where's that? It's right here. Why it didn't work? But essentially that's the RAM 0, right? RAM 0 right here. So we selected that macro and we want to place it at the corner. Let's see here. Okay. So let's do this and then I'll explain. Okay, so if you look at this command, it's say, I'm gonna place this instant which is the same instant RAM 0, right? And reference core boundary, which is the core. And then it has some number here. So I'll explain that. Paste. Okay. So what it commanded was, you know, say, oh, I'm going to take that instant and place at its corner, right? And one thing I want to show, the syntax of the command is, so they have essentially three things, right? Which one is reference, right? So in this case, it's reference the core boundary, which is this box here. And then you have the horizontal reference, and then you have the vertical reference, right? So I think this is wrong here. It's supposed to be one, but still work. So, but to make it correctly, it should be one. So essentially, so you have the horizontal edge separate. That means it has three number, right? It's say, well, what is the reference edge that I'm referring to? In this case, it's 1, which is the top one. So this is the square. So you count clockwise from the bottom left. So it's 0, 1. So the top one is 1, and then the offset is -30, right? So if I go up here, I'm gonna measure it. It should be 30. Yeah, it's yeah. If it line up, then it should be 30 right there. So I'm gonna show you the picture. I think we already show it how the edge get number. It's from the bottom left, and then clockwise. And then the same thing here is for the vertical, it's gonna be 2 and 2, which is the right side. If they measure from here, which is the reference side 2, right? The edge 2 to here is 30 as well, right? So let's do another one here. And you don't have to do like one at a time. You can do multiple, right? So I think that's what they try to do here. Is create a floor plan. So they're gonna do the 9, 2, and 3. So instead of do one macro, they're gonna do 3, right? So and the reference is the RAM 0, which is this one, right? The one that we just placed. So we're gonna place, by looking at this, we're gonna place 3 more macros reference to the first one, right? And then we have a reference type object. See, the first one we did was reference type the core, right? So now, no, we're not gonna reference the core. We're gonna reference the object, right? So, and that's the object we reference, which is the RAM 0, right? So, and here the same, right? So instead of you have one set, now we have 3 set, right? We have the 3, that's the edge number 3, and then that's the offset. So let's do this. We're gonna rerun this again. That's why. Sorry, I need to do this one. Okay. So as you can see, we're gonna, we look at it, we say, well, let's investigate some of these, zoom in here. So we have the instant 9, 2, and 3, right? Just like that. That's the order. So we can say place, the first one is 9, and then we have 2, and then we have 3, right? And it's reference the first one, which is the RAM 0. Object, object, object. And then we have edge number 3, which is the bottom, right? So what it does, what it's saying here is that I'm going to reference the bottom of the preference respect to the edge 1, which is the top, right? So what it's saying is right here, right? So I want to place my object below the reference object with the spacing of 32.52, right? So if I measure it here, right, it's going to be 32.52. So that's what it does. So okay, any questions so far? So because the next set of object is very similar. So we do that, and then let's see this here. I'll to do another one here. Yeah, sometimes escalate slow. Okay, let's zoom out. Let's see what attracted you. Okay, so now instead of going this way, it's referring, horizontally instead of vertically. So we can see here just to verify. So we do the first instant in 13, 8, and then 12. Actually, in this case, they do 4, right? 13, 8, 12, and 16, right? Oh, you can see it here, 13, 8, 12, and 16, right? And then you can compare, look at the reference type is object, and the reference object is the first one, 13. So it's reference the first one has to be 0, right? Right. So essentially the first one reference the 0, the second one reference the first, and vice versa, right? Essentially the instant just reference the one that on the right. And as you can see here is the horizontal. Gonna be 1 and 1. So essentially that the top, right? So essentially say, if I look at the top edge of my reference and I look at my top edge, the offset is 0, right? Essentially that's, I align the top edge here. So everything is flat, like flush on the top. And for the vertical separation, I'm gonna reference the 0, which is the left side of the reference object, right? So which is this side here. So the left side of my object. And then I'm gonna look at my right side as number 2, right? So remember if we count 0, 1, 2. So and reference the left side of the reference object. And I'm looking at my right side and say the offset is 36.3, right? So if I zoom in here and I measure from, because it's minus because it go to the left, right? So I had to measure this way. That's why it's minus. Right, 36.3. So, and that's, and then if you want, you can rotate it. In this case, just R0, which is the default orientation, right? So I think I have a slide talking about here. So you look at this, you have like R0, which means rotate 0. That means not rotating, right? So that's the origin. That's R0. And then you have what they call MX, which is mirror along the X exit, right through X exit here. So imagine that you have an X here and you flip it. So one way is say, okay, I'm gonna flip it, reference the X, and then MY is the same way, flip it, to the Y exit. And here rotate 180, right? So you take the R0, you rotate 180, you get this, right? So this MX90, right? So you take this. So it's here, you can reference, and then you try to make, yeah, kind of like make get used to it. But here is the system, how they number the edge, right? So for a square, it's very straightforward. You start with the lowest left corner, right? And then you say, well, I'm going to do clockwise, 0, 1, 2, and 3. For complicated polygon, you have to do kind of similar. You look at the lowest edge, and then you look at the left one. You start here, right? Not here, right? Because this is not the lowest, right? So you want to do it here, and then you start counting, right? So and then okay, so here they have some example here. So in this case, we want to place the instant A. In this case, that's the box here, right? And then a reference the core boundary. That's what we have here, right? The core boundary here just like 0, 1, 2, 3, 4. And similarly, it's count from 0, 1, 2, 3 here. And you can see here the horizontal edge separation is 5, right? So because it's the core, that's the 5 of the core. And the same thing for the instant A is 5. And it's a plus 10. That means we go in this way, right? That means instant A is on the top. This edge is above. When it's a plus side, that means it's above, right? And for the vertical, it's 4 and 4 with this one, right? And then it's minus 20. That means the instant A is on the left side of the reference edge, right? If you do a plus 20, then it's going to be over here, right? So why we need to do the relative placement, right? The nice thing about relative placement is, let's say you're gonna resize your core, and then all this placement you don't have to change, right? Because the first instant here is reference to the core, right? This corner, and everything else is gonna be reference to that. So even though you keep resizing your core based on, let's say, when your netlist change dynamically, your core gonna change, but you want to keep your placement exactly the same, right? So instead of go in and figure out, what's the new coordinate, you don't have to do that, right? You just run exactly the same script, and it's gonna place your macro relatively exactly the same respect to this corner, right? So you have to choose, essentially you have to choose the anchor point, and everything gonna be fixed relatively according to that anchor. So that's the reason we do the relative placement. It's very powerful, right? let's see. So we get that. I think the other statement is, I think it's the same. Let's see. So 1, 2, I think I did 1, 2. Yeah, sorry, just it's very slow. So I'm gonna do something here. Yeah, I'm not gonna copy. I'm gonna source the whole thing because I have to comment this out because I don't want to do it again. So yeah, I don't want to copy it. So I'm gonna run place. Just want to show you what if you're gonna copy all those files and then run it, then what it's gonna look like. Okay, so as you can see, it's the same thing, right? So by looking at the arrow, we know, right? So we had the RAM 0 here. The first thing we did was down, right? So essentially we create this column on the right side, and then we say, oh, I'm going to do 1 row, 2 row, 3 row, and another row, right? That's what, if you look in the tickle file, that's what it does. How about these, right? These doesn't have any relative placement at all. So let's see, where's that come from then? Yeah, so essentially it's have the absolute coordinate, right? So say, yeah, I'm gonna place this peripheral 1 pH at 300, so it's placed right here. So if we click on that, macro, and then you can do a Q, right? Which is pull up the attribute, and you should be able to verify. Oh, it's right there. I'm sorry. 370, right? And 1606.45, right? That's the origin right here, right? And it's R0 and it's fixed. So essentially fixed mean whatever we do in the later step, the tool not gonna move the macro. Essentially it's whatever we want to place it there, the tool not gonna move it. So that the big one. How about the smaller one? So I assume it's gonna be in this place instant. So let me see. So it should be okay. So place instant here. So let me pull that up. Right. So these are the smaller macro, right? It's same thing, right? It start with the X is 385. The 4 of them here, 5 of them. So you can say, oh, it must be these 5, right? So right here, 1, 2, 3, 4, 5, right? So the first 4, that's 5, and then 8. 841 right here, 841, right? You can see the coordinate here, by, just moving around, and you already know which one corresponding to this. And then the biggest one is 1674, I believe this one, right? Right, so that's it. So majority of the RAM placed on relatively on the right corner, right? And then these kind of like anchor to the left. And then you see later on later step, I think we're gonna do on Friday. Why we do that? Because sometimes, as I mentioned, right? So we want the ability to resize the core, right? So essentially you have to anchor all these macro at certain corner, and then you can resize your core accordingly. Okay, I think what else I want to do. I think that's very much it. And here, I mean, yeah, when you place a macro, you can associate what's the placement status, right? So we have fix. That's what it does. Fix it, right? Don't move it. And then we have soft fix, right? So you can read all here. And then the toolbox, yeah, let's do that quickly. So so if you notice, there's a toolbox here, right? So this toolbox is very useful to align things. So let me see, I can move it over here. So let's just do a quick example here. I don't think we have, okay. I gotta move this way. Okay, so for some reason, I don't want these two to be here. I want it to be aligned to the top. You know, say, so I'm gonna say, okay, I'm gonna move this bigger macro, you know, align flush on the top. So I can select these, and you can see here that I'm gonna look at the align portion here, and you can tell, so this is the align top, right? That's, in this case, that's what we want. So it's gonna move to the top, right? And then I wanna move, let's say I wanna move this up, but I wanna keep a certain distance, right? So space here. So I wanna, let's say, make it 20. And the distance I want to respect to the top one. So essentially I want to move the second up and then keep a distance of 20. So let's try that. Let's say right here. Say try. Right. So if I come in here and let's say, should I measure it? Right, it's going to be exactly 20. So there's multiple option you can do, but just want to show you. And then you can, yeah, you very much can do anything. You don't have to do relative placement. You can do all these array with these box, right? Very straightforward. Just slide them up very easily. Okay, so I think we have only like 2 minutes, so I want to leave that for does any question. Is there any question? Let me look at it. Hello, no question?
Doesn't look like it.
Okay. So
Dạ, cảm ơn mọi người. Thì nếu mà có câu hỏi gì thì cứ có thể là trong cái lớp học nó có cái stream đó, thì các em muốn hỏi gì thì cứ để lên trên đó hỏi cũng được, hoặc là gửi email đến cho các thầy để hỏi, giống như có một số em đã hỏi. Okay, Thiện, there's a question in the chat.
Oh yeah, that's the coordinate. So I think he's talking about this one here. So essentially the statement here is a place instant, right? So place instant is you take an instant name and then an X and Y, right? So in this case, so I think we already established, oh, the C380, the smallest one. So it has to be the bottom one here. So if I move here, right, that's 385 and 937. So yes, that's the X and Y of the of the of the macro. Yeah. Yeah, only this corner. Yep.
Ok, để cho mọi người khỏi yên tâm nha, nếu mà không hiểu về ESD nhiều thì cũng không sao, thường thường trong cái chip có một người ta lo chuyện đó. Mình chỉ lo bỏ mấy cái path đồ vào thôi, chứ mình hiểu ESD để cho mình biết cái nguyên lý, những cái lý thuyết đằng sau thôi, chứ mình không có cần phải hiểu để mà lo trách nhiệm của người PD. Không 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 có cần phải lo nhiều về PhD, về ESD. Còn về laptop thì giờ mình chỉ có mấy cái design rule là mình biết hết. Sau đó khi mà qua place mình sẽ hiểu hơn về cái laptop.
Yeah, so there's a question about if we change the core area, whether these spacing between these group of relative placement gonna change. No, because the way we specify is about spacing between them, right? So it's not gonna change, right? So and talking about fixed. So I mean, ideally, all of these macro has to be fixed, right? So we don't want to move them, right? So initially, like let's say that the first time you want to run the placement, you don't know, right? Say initially when you do work on a chip, you don't know why this RAM has to be here, right? It can be why it has to be in this corner, right? But not this corner, right? So there's way you can run the tool by let the tool actually float, place the macro for you, right? So at least you have some idea of what the tool thing, what's the macro gonna be, right? So you're gonna use that at the starting point, right? At least say, wow, the root of macro, you know, these ramps should be in this corner instead of this corner. The reason is that the tool know the connectivity, right? So if this RAM, interfacing with a lot of I/O over here, so more likely the tool gonna place the RAM here, right, next to the I/O, right? But again, that's just one factor, right? Whether that's this RAM talk to the other RAM or a lot of logic, right? So, but after you know where's the RAM placement, yes, you have to fix them, right? You don't want later step to move the macro. So I think those are the old questions they have.
Yeah.
All right.
Yep.
and make sure this is just because these lab take a long time to do. So I'm just show you some of the activity, but in here, so remember that I have this orange. Yes, do these right in the lab. So it's going to take you some time to do it. So okay.
All right. We 3 minutes past. Cảm ơn mọi người rất nhiều. Chúc mọi người có một ngày vui vẻ và học hành tấn tới.
Ok, thôi cảm ơn mọi người nha. Ok, bye bye.
Thank you. Bye.
Right. Thank you. Bye.
Cảm ơn chị
Bye bye.
Kiều. Cảm ơn mọi người.
Recording stopped.